All right, let's get started. So I'm here to introduce to you perhaps one of the most exciting things to come to MongoDB 4.2. And like any exciting new feature, the best way to show it is with a demonstration. So sit back and brace yourselves for possibly one of the most intense things you're going to see at this conference. And it's only 3 steps. Step 1, we insert a document into our collection call with name Doris and her social security number, which she wants to keep very secret. Step 2, we do a find one on that collection, querying by that social security number, and store it in a variable named doc. Step 3, we print doc to standard out, and we get back the document that we inserted. And that is the entire demonstration of this new feature, because this is client-side encryption, where everything happens in the background. That was a bit of a joke, but it's late, I get it. So when you write code that looks like this, if you have client-side encryption enabled and you mark SSN as a sensitive field, the driver, your MongoDB 4.2 driver, will automatically encrypt the value of SSN before sending it to the server. And on the flip side, whenever the driver receives a document containing that encrypted ciphertext, it will automatically decrypt it and return it to you as you inserted it. But encryption is not a new concept in MongoDB. We already have encryption in transit with TLS and encryption at rest with the encrypted storage engine. So how does client-side encryption kind of fit in all this? And to discuss it, here's a super simple model of what happens through the life of an insert, starting at the client, over the network to the MongoDB server, down to disk. What are some basic attacks somebody could do if you didn't have any auth or any encryption enabled? Well, if you had absolutely nothing, the simplest thing is if an attacker knew your host name, they could simply connect to your MongoDB and query the collection for the SSN. Obviously, enable auth. Maybe a little bit more subtle is they could snoop the network traffic between your client and MongoDB and get the SSN from the insert command because it's sent in plain text. So enable TLS to encrypt your network traffic between your client and MongoDB to prevent against that. An attacker could try to pose themselves as a MongoDB server, but fortunately TLS also validates the identity of the server using certificate authority, so TLS protects against this. What if an attacker were to somehow get access to your disk, and since your data is persistent in plain text, they could scrape the disk for that unencrypted SSN? Well, the encrypted storage engine protects against just this. It will encrypt before persisting. But perhaps the most scary is what if an attacker was a malicious administrator? They had root credentials to your MongoDB server. Well, it's kind of game over at that point. Like, they could do anything that any administrator could do. So they could certainly query any collection and get the unencrypted SSN. But this is the very thing that client-side encryption protects against. It makes it impossible for somebody who only has access to your MongoDB server to decrypt this data, because the encryption keys are protected with an external service. So really, this is about shrinking the boundary of an unencrypted data. With nothing, with no encryption enabled, the unencrypted SSN lives throughout this entire flowchart. When you enable the encrypted storage engine, we shrink this down to just between the client and MongoDB. When you enable TLS, we shrink this to just within the client and just within MongoDB. And client-side encryption shrinks this to the tightest bound of all, just within the client. But client-side encryption is not meant to replace TLS or auth or the encrypted storage engine, but really meant just for your most sensitive data, your most sensitive user data, and meant to work in tandem with these. Because if you're encrypting things in the client and the MongoDB server doesn't know how to decrypt it, you're inherently limiting what you can do with that data on the MongoDB server. There are some things you could do. You can do a complete replace of an encrypted value. This is like taking one black box and replacing it with another black box. So on the driver side, we will encrypt the value of SSN here, and on the server side, we'll completely replace the bin data that was encrypted with a new encrypted bin data. But any operation that requires knowing the contents of the data will obviously have to error. For example, this aggregate tries to make a new field, name SSN, by concatenating the name and the value of SSN. If SSN is encrypted client side, then when the server receives this, it can't sensibly concatenate the SSN with name because SSN it just sees as a ciphertext. So you would get an error for this. But what might be surprising is that you can actually query unencrypted fields if you're encrypting them deterministically. So if you're using deterministic encryption, the same plaintext encrypts the same ciphertext, so we can actually sensibly respond to these queries. The bin data would match. And this is actually pretty incredible because this requires, on the client side, knowing enough about the MongoDB query language to know exactly what values to encrypt. So in a little bit more of a complicated find query, we know exactly to encrypt the 2 values in the $in query. So the driver will produce this before sending it. So that's a rundown of how it works. But why would you want to bother with this? If you're trying to protect against the attack where an attacker has complete control over your MongoDB server, it's kind of like game over at that point. But there really are 2 compelling reasons. And the first reason is quite common. You're storing private user data in a public cloud, and you don't have complete control over where that data is hosted. And I kind of like to use an analogy for this, which we're going to use throughout the talk. It's kind of like storing your stuff in a storage locker that you pay rent for, but ultimately you do not have complete ownership of. And it's owned by somebody else. Since we're going to be coming back to this analogy, we're going to give her a name. We're going to call her Doris. And you might trust Doris, but you also might be storing some very sensitive stuff in your locker. Maybe your childhood diary, and you really don't want her or anybody else to see it. But she has the master key to your locker, and so you're implicitly trusting her to not mishandle it, maybe like by leaving it unlocked at night, but also her authority could be overruled. Maybe a police officer comes with a search warrant, and she has no choice but to give them access to your locker. So maybe this keeps you up at night. And you really want to only have, make it so that only you have access to your diary. So as a way to protect against that, you take your diary, you put it in a small vault to which only you have the key, and then you put that vault in your storage locker. This is pretty much client-side encryption. Like, MongoDB will store your stuff, and it doesn't matter what that stuff is, even if it doesn't know how to decrypt that stuff, and you keep the encryption keys only accessible from within the client. But Doris could still do some things. She could take that vault, throw it outside of the locker. You would never have access to it again. She could replace it with a new vault. She could destroy the contents inside, maybe by starting a small fire under the vault. And this is similar to what could possibly happen when you still have client-side encryption enabled. If somebody has access to your database, they could still delete your data, make it unrecoverable, swap it around. Ultimately, they cannot read it, though. The second compelling reason to use client-side encryption is to make a way to support the GDPR right to be forgotten clause. And this roughly states that you have to provably delete user data if they request it within some time frame. And client-side encryption makes this simpler to do because you can associate encryption keys with specific user data. So all you need to do to make user data unrecoverable is to delete their encryption key. Cool. But how do you actually use client-side encryption? It is available in beta in the Java, Node, and Python drivers currently, and they all have a similar type of configuration. And that is on the Mongo client, the top-level client you use to connect to your MongoDB cluster. So I've hidden away some of the sub-options here, but to configure it, you use this auto-encryption opts, and we're going to use the analogy to kind of discuss the sub-options since they're a little bit tricky. For one, going back to the analogy, it's likely that you have stuff in your storage locker that is not worth the overhead of putting it in a small vault because you have to do extra work every time you want to retrieve and put something in a vault. Like your, I don't know, basketball, chair, and plant or whatever doesn't require putting in an extra vault. And in addition, you might have multiple things that are sensitive, multiple vaults, and it's up to you how you want to identify what keys open what vaults. You might want one key that opens up all vaults, or you might be sharing this storage locker with a partner, and maybe you want a key for each of you to open up your own vaults. So similarly, your data probably only has a small subset that is sensitive enough to require client-side encryption. And it's up to you to associate keys with that data. So that brings us to our first configuration step, which is the JSON schema. And a JSON schema normally is a kind of meta JSON document that describes the structure and types within a JSON document. So this example schema describes a document containing two fields, A and B, A being integer maximum value 10, and B being a string. So this matches a document look like this, but will not match against a document like this, because this is an integer greater than 10, and B is not a string. In MongoDB 4.2, we've further extended our implementation of JSON schema to introduce an encrypt subdocument. And so this tells us that you want to enable client-side encryption on this field. You identify three things within this encrypt document. The key ID, which identifies the key to use for encryption. The algorithm, how you want to encrypt. This could either be deterministic or random. And the underlying BSON type of the field that you're encrypting. You configure this client-side using a sub-option of that top-level options on the Mongo client called schema map. And this maps collection namespaces to JSON schemas. This might be surprising if you've used JSON schema before, because before 4.2, JSON schema was only a server thing. You would only use it when creating a collection to validate server-side. And you could still do that with this encrypt subdocument, but it's really just a fallback. So you could still do db.createCollection and use a JSON schema that contains the encrypt subdocument, and we will still respect it in that if a client, say it was misconfigured and was sending plain text when it should have been sending encrypted data, the server will reject that plain text saying, oh, I expected ciphertext. But this is really just a fallback, because the threat model that we're protecting against, where somebody has full control over your database, they could certainly subvert that. They can just gladly accept, they could drop the schema and gladly accept any plain text that's sent. So this is certainly just a fallback. So that brings us to our next sub-option. And jumping back to the analogy, as you add more vaults to your storage locker, the amount of keys that you get becomes unmanageable. And so you want to put these keys somewhere that makes it convenient to access and to which only you have access. But we've already solved this problem, so we can do the same thing. We take all those keys, we put those in a specially designated vault to which only you have the key, and then we put that back in our storage locker. So we've added an extra step. In order to retrieve your diary or any other sensitive things, you need to first open up this key vault, get keys to the other vaults, and then open up those other vaults to get your items. But now you only have one key to manage. And this is kind of the motivation for the second step, which is the key vault collection. And this is a specially designated MongoDB collection that contains your encryption keys. This might sound fishy, because if we're storing your encryption keys in MongoDB, doesn't that mean somebody who has access to MongoDB also has access to your encryption keys? But in reality, these keys are stored after being encrypted with an external service. So even somebody who has access to your key vault collection does not have access to your like the underlying key material of those keys. You configure it by setting the key vault namespace on the Mongo client, the sub option, and since we will do find queries whenever we need to do encryption automatically, you need to just have like the read role on this collection. But there are some scenarios you have to consider. What if somebody were to drop the key vault collection? And this is similar to if Doris were to take your key vault and throw it outside of your storage locker. Well, there is one thing you could do about this, and this is you could put your key vault collection on a different MongoDB cluster. maybe one to which you have complete control over. And you can do this by setting the key vault client to another Mongo client. And we come to our last configuration step, which is that external service that protects our encryption keys, which is KMS, or Key Management Service. Much like the key vault key protects the key vault, KMS protects all of your keys in the key vault collection. And this is kind of the crux of client-side encryption. Encryption and decryption requires both access to MongoDB and this external KMS service, to which only the client should have. You configure KMS with this KMS provider sub-option, and right now we support AWS KMS and a local KMS, and possibly more in the future, depending on demand. And that's it. That's all of the top-level configuration. So let's recap, going back to our original example, to see what was really going on in the background when we do this insert. The first thing that really happens in the driver is that we will compare this insert command against the JSON schema for this collection call. We'll see that SSN is actually a field that should be encrypted, so we will get the encryption key associated with that field. That key comes to us encrypted. We send that key to KMS to decrypt it. Then we encrypt the value that we want to encrypt, and then finally send that insert with the encrypted bin data to MongoDB. That happens all within the client. So that's a pretty high-level overview of how it works. There are a few fine print things I want to cover. The first being the encryption algorithm that we're using. And this is authenticated encryption with associated data using the advanced encryption standard with cipher blockchain and hash-based message authentication code using the secure hash algorithm, or the easy-to-remember AEAD AES 256 CBC HMAC SHA-512. And since this is authenticated encryption, provides both confidentiality and integrity. If somebody were to modify it, we would know. And there are two modes, all those abbreviations dash deterministic, and then all those abbreviations dash random, which you unfortunately have to type out in the JSON schema. And the only difference is really how they're seeded. So random is seeded with a random IV. So if you encrypt the same value twice, you will get different ciphertexts. And deterministic, as you would expect, when you encrypt the same value twice, you get the same ciphertext. And because of this, as I mentioned earlier, you can query on deterministically encrypted fields with exact matching. Like you can't do a range query, but you could do a query like this that matches SSN with an exact value. So we'll still be able to respond correctly since the ciphertext matches what's on the server. But there is a caveat in that we only support this for binary comparable types. What I mean is, right now this query, if you were to run against an unencrypted collection, could return a few different things. A with B containing a double 1. This could return A with B containing an integer, A with B containing a long, and A with B containing a double, the exact match. But these all have different binary representations. So if we were to allow encrypting field A, then we would still, even if this was deterministic encryption, get different ciphertexts. So if we were to allow this, we would only respond with the one that is an exact binary match, which would change query semantics. So for BSON types that would change query semantics, we explicitly prohibit this. The next fine print point I want to make is the ciphertext itself. And this is stored in an existing BSON type, the bin data or binary type. But we've introduced a new subtype 6. And this represents a field that was encrypted with client-side encryption. But since this is just a new subtype, old drivers and old servers won't like croak if they see this. They'll just treat it as a black box. But this will indicate to a 4.2 driver that it is a client-side encrypted field. So if you have it enabled, it will automatically decrypt. The actual layout of the bytes in the ciphertext is as follows. First byte is the algorithm, either 1 or 2, indicating random or deterministic. The next 16 bytes identifies the UUID of the key that was used to encrypt, followed by a single byte for the original underlying BSON type, and then the result of the block cipher. So there are a few things worth noting. One, since we include both the algorithm and the key ID, the ciphertext describes how to decrypt it. So even if your ciphertext were to move, like you projected it out, you copy-pasted it somewhere, whatever, within the ciphertext there's enough information to decrypt it, assuming you still have access to your key vault. We exposed the original BSON type of what was encrypted, so we can do extra validation. So if you were to encrypt the wrong BSON type, we would know. But as a caveat of this, any BSON type that is like a single value type where the type itself is the payload, like min key, max key, undefined, or null, is explicitly prohibited because encrypting it would hide nothing. And similarly, Boolean deterministically encrypting a Boolean is prohibited because it would just take two values and move it to two other values. And the payload itself, since this includes the IV, the HMAC, and is padded to the 256-bit block, this can introduce up to 66 to 82 bytes of overhead, which might be non-trivial, especially if you're encrypting small values like in 32s. Okay. Next thing is a new top-level class that 4.2 drivers come with, the client encryption class. And this is kind of a helper utility class. It does three things. You configure it similarly to how you configure the Mongo client for automatic encryption, but you can use it to create new encryption keys, which will insert automatically into your key vault collection. You can use it to explicitly encrypt a field, or a value, sorry. And on the flip side, explicitly decrypt a value. And this comes in handy when you need to bypass automatic encryption, which is necessary because we can't always sensibly automatically encrypt things for you. There are two main reasons. One, we haven't implemented everything yet. And two, sometimes it's impossible. So we always err on the side of safety because we don't want to risk sending unencrypted data when you meant to send encrypted data. So if we don't know how to parse it or it's impossible to know what you want, then we will throw an error. And in that case, you can bypass automatic encryption and use explicit encryption. So here's an instance of where it's actually impossible. Suppose you have a collection containing these three documents where passport num and the SSN are encrypted with different keys. And you have a query that looks like, or an aggregate, where you first project into a new field identifier, and identifier is set to SSN if it's not null, otherwise passport num. And then you match on that new field identifier by this constant. So when we see that, and we try to automatically encrypt it, we know that this constant should be encrypted because it's going to be one of two encrypted fields, but we don't know which key to use because it could have come from either field, and we don't know until if it's been sent to the server and is actually seeing your server, the data that's on the server. So in this case, we would actually error client side because we don't want to risk using the wrong key or, God forbid, sending plain text. So as a workaround, you can bypass automatic encryption. And since the ciphertext includes enough information to automatically decrypt, this just bypasses the automatic encryption, but you could still decrypt results. And with bypassing, you can tell us exactly how you wanted to encrypt that constant. So use the client encryption object, .encrypt, and then give us the key ID of what you want to encrypt with and the algorithm. So next are the keys themselves. What happens when you insert data keys into the key vault? They're documents that look like this, and the noteworthy thing here is that they are identified in one of two ways, either the underscore ID, which is a UUID that we generate for you when you use the client encryption object to create a data key, or alternate names or labels that you can use to refer to keys in an easier way and also associate keys with user data. The key material itself, as I mentioned before, is encrypted with KMS. Cool. So that covers all the fine print stuff. And I want to go back to an example. So Doris here notices what we've been up to with our scheme of putting things in vaults, and she gets an idea because she sees how much we value our privacy. Her idea is to create a web app called Mongo Diary. It's a microblogging service where privacy is the top priority. And we're going to walk through what Doris does to build 4 simple pages: a login page, a page to create posts, a page to view posts, and most importantly, functionality for users to delete all their user data, provably and quickly. So she has the right ingredients. She has MongoDB in the cloud and KMS. The first thing she needs to do is create a key to use for encryption. So she writes a one-off script that uses that client encryption object, calls create data key, and then prints out the resulting ID. So for the sake of example, we're going to say that ID is 609. In the login page, the user documents are going to look pretty simple, just having an email, password, and a list of users they follow. So we want to automatically encrypt the email and password, but when we do a login, we'll need to query by the email. So we use deterministic encryption for the email and the more secure random encryption for the password, and both use the key ID that we used when creating the key initially. Next, we start writing some code. The register function becomes super simple with client-side encryption. All you do is insert into that collection as you normally would, and email and password are automatically encrypted. Login, similarly, is able to query on email since it's deterministically encrypted, and then matches on password after. But it's hard to tell that anything is going on. So as a sanity check, Doris writes another one-off script that uses a client without client-side encryption to dump out the contents of users. And sure enough, she sees that email and password are stored as ciphertext. So next up, she writes the create post page. And posts are going to contain a title, a body, which people want to keep encrypted, date, and a user ID. So since body is the most sensitive thing, we create a JSON schema to randomly encrypt it with that key that we created in the beginning, 609. The create post function is nothing surprising. We insert into the post collection. But though this seems straightforward, we're going to have to revisit this later, because as we start to implement the delete my data function, we realize that what we have might need to change. Initially, the delete my data function just deletes everything from posts querying by the user ID. But suppose that the cloud provider is taking backups of this collection daily. This won't be enough to completely erase user data. What we'd rather have is one thing to delete, which is we'd rather just associate an encryption key with user data and delete that. But right now, we're using the same encryption key for all user data, so we want to split this out. In order to do that, we need to modify the register function to create a data key every time a user registers that's associated with this user ID. So we modify this, and note that we set a key alt name or key label to that user ID. And this allows us to identify a key and associate it with a user. Next, we update the schema for the post collection. Instead of that fixed 609 key ID, we set it to the string user ID. And what this tells us is anytime something's inserted into the post collection, it will look up from the key vault using the value of the user ID field. So this string is like a JSON pointer. And now we can modify delete user data to delete directly from the key vault using the key alt names. And the key vault could be on a separate MongoDB cluster, or configured with different backup settings so that it's easier to verify that data truly has been deleted. And lastly, Doris builds out the homepage, which is a list of posts from users that you follow. The function for that is pretty simple. It just does a find many, querying on the array of followers in your user document. But since we've changed it such that posts have, or users have their own keys, this could potentially return documents from 20 different users, which means 20 different encryption keys. And the driver will automatically decrypt those values even if you're not using them. So even if we're only printing out the title and the date, we're still getting the encrypted body. So in this case, it makes sense to project out the body if we're not going to use it, so we don't have to pay the cost of automatically decrypting it. Great. So Mongo Diary is finally complete, all of our 4 pages. And Doris puts Mongo Diary up live, and it becomes popular amongst the users of the most valuable and private information, dissident journalists, and angsty teens. And the user base grows, so much so that Doris needs to set up zone-based sharding to spread out traffic globally. But unfortunately, one of those shards is located in East Dictatorland, who seizes control over one of those shards and starts reading through the data. Her users begin to worry, but she reassures them that since this was encrypted client-side, there's no way that East Dictatorland can read the contents of their posts. So if you're responsible for private user data, ask yourself what would happen in a scenario where your user's most sensitive data became exposed, and if you're protected against this. And if not, consider enabling client-side encryption. And that is all I have.